Welcome to Antenna as a Component. Today we are with another topic, which is effective aperture area. This time we will understand what is effective aperture area and how to derive the relation between the effective aperture area and the gain of an antenna. So, what is effective aperture area? Simply, if we have bar coming from somewhere in form of bar density in the free space landing on our antenna, and our antenna is feeding a load RL, and RL has a power received BREC. So effective aperture area is how the power is converted from power density to the power received, and simply can be calculated as the ratio between power received to power density. And why it is important? Because it is related to the antenna gain as A effective equal to lambda squared over 4 pi multiplied by the gain. And this actually equation is fundamental in describing how the antenna receives power. And together in this presentation or this video, we'll understand how to make this relation. To prove the relation between the gain and the aperture area, we will use the antenna transmitting mode to find a relation between the antenna effective length HE and the gain, and then we will use the antenna receiving mode to find a relation between the antenna effective length and the effective aperture area. Here we will start with the electric field equation, and generally electric field equation will be a function of the current and the effective length of the antenna, and simply effective length of antenna is equal to the length of the antenna multiplied by some function of theta and phi, and this function is simply some sort of sines and cosines. Then we will use this equation to substitute in the power density equation, which is BD equal to magnitude E squared over 2 eta naught, and eta naught is just the free space wave impedance, which is equal to 120 ohms. And then simply by simplifying what we have here, we will reach this final equation, a relation between the power density, the current, and the effective length. Now we will calculate the total power radiated from the antenna based on the power density equation which we have determined in the previous slide. By substituting in the power radiated is equal to double integral of power density r squared d omega, and omega is the Newton's angle. Then follow with the integration steps until we reach equation 1. Then we have actually or we can calculate the power radiation using another equation, which is this equation 2. From where this come from? Simply if we assume that the radiation resistance has a current following through it is I naught. Of course, this assumes that the antenna is at its resonance. Then by calculating V naught equal to I naught R radiation, multiply voltage with current, you can get this equation, and we divide by half to account for the RMS value. Then equate equation 1 and equation 2, make reformulation in this step, you can get a relation for the double integral of HE squared d omega. Then we go to the gain definition. which is G equal to 4 by mu, 4 by U divided by double integral of U d omega. And U is actually a function or not, it's proportional to HE squared. So we can replace the terms. Instead of U, we can use the HE. Then we use the result which we have achieved here to find a relation between the gain and HE squared. Now we move to the antenna receiving mode, and actually this is much easier than the antenna transmitting mode. Simply we will assume that we already received the power, and this power have generated some voltage, and it has of course some radiation resistance or internal resistance Ra, as can be shown here. And we want to supply this power to some specific load RL. What will be the relation between voltage and electric field coming from the antenna? Simply, the voltage is equal to the electric field multiplied by the effective length of the antenna. And what is the relation between the voltage across the load and this voltage? Simply, you have a voltage divider, so your volt VL equal to RL, the resistance which you would like to calculate the voltage on, and divided by the two resistances which are RA and RL. Simply this will reduce to half of VA. And why? Because we are assuming maximum power transfer, meaning that RA equal to RL. Then we want to calculate the power received. This is our interest. So what is the power received? Power received is simply half multiplied by the voltage squared divided by RL. Half this represent the RMS value, and just by replacing what we have reached here in this equation and making some simplification, we will get some relation between the received power, the electric field, and the effective length. And in this specific equation, we have make another assumption that our antenna is lossless, means our antenna is just the R radiation. Simply, what we have make an approximation is in total RL is equal RA is equal to R radiation. Now we revisit our aperture area definition from the first slide and reformulate it a little bit in form of the power received is equal to the effective aperture area multiplied by the power density. Then we will recall that our power density is simply magnitude of the electric field squared over 2 eta naught. We substitute here, then we will get the equation in the other side. And from the previous slide, we have another equation that relate the power received with the effective length. And then comparing the two equations together, we can simplify that the effective aperture area is a function also of the effective length. So now we are bringing everything together. This was the summary of the transmitting mode of the antenna, the relation between the effective length and the gain. And this was the summary of the receiving antenna mode, which is the relation between the effective aperture area and the effective length. We will reformulate A in this way. Then we will use it to substitute in equation B, and we will then make cancellation of common terms. Once we do so, you will find the magic happen, and you can get the relation between the effective aperture area and the gain as A effective equal to lambda squared over 4 pi multiplied by G, which is the gain. Thank you.